is Dr. Ilgmārs Eglītis, and together with Kristers Nagainis, the perspectives of research on small bodies of the solar system in Baldone Observatory. Do you need any help?
Yes, presentation.
Laikam vajag uzlikt.
Viņa te ir.
Vai šis ir jūs?
Nē, tas nav. Tev tu liekupēji. Jā.
Yeah. From the two authors, Ilgmārs will make the presentation. Yeah.
Okay. Now I say some words about perspectives of research in Baldone observatories on small bodies of solar system. At Baldone, astronomers work with a Schmidt-type telescope, 1 meter in diameter, and entrance 80 centimeters. We have installed two CCDs in focal plane, each cover 1 square degrees about on the sky, and similar CCDs, cameras, STX, and AC Aluma. The pixels size is 9 to 9 microns, and linear sizes of the CCDs is 4096 to 4094 pixels. The results of the monitoring from 2008 to 2023 gave 149 new discoveries of asteroids, and the most important is two. It is a Apollo type asteroid Saule. Asteroid distance is of this object is only 600 of astronomical unit, and the second is a great 32 kilometers diameter Centaur type object Orius, distance from the sun about 12.44 astronomical units. Here is a list of the asteroids names, which gives from Baldone, and it is 12 objects, and the last is a object for which name awarded at 2024. It is connected with the FOTONIKA-LV, and in recognition of achievements of national science platform FOTONIKA-LV, and towards the consolidation of human capitals in quantum sciences, space sciences, technologies, and progress in the international cooperation. Now we work with about monitoring future prospects. The problem of observation of near Earth object is small sizes of objects, and very quickly go through in the sky, Therefore, it is harmless to observe these objects, and therefore need special new observation technologies. Important observation of now is a connect with the planetary defense, of course, because the small NEOs bombarded the Earth very rare, not very rare, about every 5 years, similar event as Chelyabinsk is in reality. It is a results from radar observation of bolids. And the other important, the searching and research of the NEOs is mining applications. Solving this problem of observations is a evolved synthetic tracking method, which summarizing images with a short exposure time, and we need to determine the ideal exposure time for the number of frames, influenced from the system hardware configuration, influenced from the sky background, and also influenced from the different quality of transparency in the Baltic region. This evolving this method is in progress now. Present studies of asteroids also research the characteristics of asteroids. And the starting point of this is the Baldone Observatory observations, series which we can obtain about 2-4 hours observations for object every night, and we collected about more than 100 observations for each object, with accuracy about 500 magnitude. The second possibilities is obtain the position magnitude measurements from the archive of the Minor Planet Center, which collected more than billion observations of different objects, asteroids, from 1934. But the accuracy is less, often 0.1 magnitude, because many of observations made by photographic methods. But we have a good statistics for even per asteroids, because we have the brightness measurements more than 1,000 for each asteroid. The list of observer of asteroids was compiled, of course, from Minor Planet Center, MPC checker, and we obtain also LightCare database, and we select NEO and Asmoid asteroids with distances less than 1.3 astronomic unit and greater than 18 magnitudes without period data. And these observations give possibility to obtain the rotation period. Here is a schematic data reduction and processing schema, mainly from, of course, Baldone and MPC, Minor Planet Center data. At first, we selected observations from observatories different, which has more than 70 observations of each object. And as a rule, this is about 12 till 15 observatories for each object. This scheme is for practically for one object, reducing and processing. And after when we selected this series of brightness observation, we constructed the phase diagram, and also we evolved this phase diagram, discarded the magnitude measurements, which is great errors by 3 sigma criterion, because minor planet data has 3 till 2 4 observations of brightness per night, and these observations is ranged in 20 till 30 years with unevenly distribution in time. And 3 sigma criterion, we adopted that in short time the brightness of asteroid not change greater than 0.5 magnitudes. After this, we make the Lomskargle analysis of phase curve, and we obtain the power spectrum from this analysis with many peaks in power spectrum, and also light curves for studied object. From many peaks, we select only this peak, which gives the same rotation period at first, which has the 2 light curves of 2 maxima and 2 minima, and the value of the in power diagram of peaks is great, more than 0.2, and the shape of this peak is somebody similar to the Gaussian. Then we obtain the weighted period, weighted from this magnitude higher, weighted by the observations number, and weighted from the dispersion around the phase curve. Of course, we have process the whole series to the first observation moment, taken in count the changes of distances, observer asteroid, asteroid sun, and phase changes also. Here you can see the data of observatories which can used in our research, and now we has an example for one asteroid. At first we has a name of observatory, code practically of observatory, and passband in which observatory is observed. And here is a period obtained from every series of this, the first observatory, and so on. Here is a value of magnitude of peaks, and here is a distribution around the phase curve, phase diagram. And here obtained weighted period from the peak value, weighted period from the number of observation here, and here the third is a period weighted from the distribution around the phase diagram. Results from this asteroid, and real rotation period is the average from these three obtained magnitudes. Here is a table for our studies, for which asteroids we can obtain the rotation period, and as you see, there is a good accuracy. The continuing of the presentation will be from Nagainis, my close collaborator. Please.
Hi, I will continue on the asteroid quantization, and many topics already have been covered, such as the phase curves, but I'll speak more about how do we actually obtain the absolute magnitude, and here you can see an example of it. So we have the data of the phase curve, so the asteroid brightness across various phases, which you can see on the x-axis. And we can see three different lines, where in this example, I want to show the comparison between the default method that the MPC database has done, which is in the blue line, where they employ a very simple model to fit this phase curve. If you see the formula down below, they use, we have 3 degrees of freedom in this one, but in the MPC database, they only use to fit only 1 degree of freedom, which is the absolute magnitude, where they fit the slope parameter G to 0.15. And we can see that this is not the best and the most accurate way to do so, because in the literature, it has been already proven that the slope parameter does change for different type of asteroids, and it's actually more accurate to use 2 different slope parameters. So to justify using a bit more complicated method, we can see the red line where the slope parameter G is left as a free parameter, and it already produces a better fit. And with the orange line, which is in this case, very similar to the red one. We leave 3 degrees of freedom for our fit model. And this is the formula that you see down below, where we have h, the absolute magnitude, the value that we want to obtain. Very important if we want to obtain, for example, the size of the asteroid, which can be done with the combination of the albedo of the asteroid. And then we have the two other 3 parameters, G1 and G2, which show the different slopes across various phases, which is the most accurate version how to model these phase curves. And we can obtain a very precise measurement of the h. We can use it for various observatories, as you can see on the diagram on the right, and we can obtain fairly similar values. And we can employ a method where we take the average method, but we can also try to combine them to get a uniform value of h, but it comes with difficulties. Why is it difficult? Because if we want to combine the brightness measurements for different observatories, we have to deal that they use different filters. So the now common approach is that we define the absolute magnitude in the V band. We don't all observe in the V band. Some are red, some are orange, and different ones. So we need to correct for that. On the right, you can see the difference between the V band and different filters. And it is very noticeable. It's important to take into account. And it's also important to see that it might be bimodal, and it might have a large distribution, that it's not a singular peak. Why? Because there's also different things that we have to take into account. For example, the bias that comes from the reference catalog that we use to calibrate the brightness of the asteroids, and of course, even the observatory bias. So all these things need to be taken into account if we combine all of the brightness measurements. And with that, we can employ methods to use all of the data from observatories to gain both the absolute magnitude and the rotation period. For the rotation period, I use a different method, because there we don't need the absolute brightness differences, but we need the relative ones. So there I actually employ the modeling of the phase curves. As you can see, the first steps is already what Ilgmārs described of the reduction. But then what we try to do is compute the phase diagram for one reference observatory, where we have a lot of very good data, which can perform a good fit. And then we shift all of the other observatories to that phase curve, which allows us to obtain a very good phase correction for our data. And from that, we can get this quite messy plot on the right, where it is actually the rotation curve with the combination of, in this case, nearly 10 different observatories. As you can see, it is not perfectly on the line of this estimated rotation curve, because there's a lot of biases which are hard to take into account. But the fact that we have performed the reduction quite well, we can still see a clear indication that this is the correct period on the left side of the diagram, which is the power spectra. And we have only 2 distinct peaks for the possible rotation period, which is 4 hours and 8 hours in this case. And we can already discard the 4 hours one, because it would be the same diagram, but just with a singular peak. And as already Ilgmārs explained before, we need a phase curve with 2 peaks, because that is what an asteroid would produce. So this is the things that we've been working on with the phase curves and the rotation curves and light curve analysis. But combining all of that together, we can also perform the light curve inversion, which helps us to find the asteroid shape. And this is quite a difficult method, which requires very good data reduction combined with a large volume of data across different times and different phases in order to observe all the discrepancies of the brightness variations, which would allow us to inverse the light curve into the shape estimation. And this is done already by a method by Castellane 20 years ago. And it allows us to obtain the convex shape of an asteroid. So let's say an approximation of the real one. And in theory, this method is very useful because it allows us to get a unique shape. With the non-convex ones, it would already be non-unique, and it brings an extra difficulty to the whole process. And also this method is very useful because the output of this method is also the orientation of the poles and of course the actual rotation period. So yes, this is the combination of all the methods explained before and even serves as a summary. And with that, I will leave you for some questions.
Thank you.